This is 9.22, dimensional collisions. Today we're going to talk about how to calculate momentum in 2 dimensions. Since we live in a 3-dimensional world, we need to talk about collisions that are not always perfectly head-on and straight. We know that when we play like pool or something, things will go off at different angles depending on how you hit it. These are called glancing collisions. And we can actually calculate this because it's still the conservation of momentum. So we're not going to talk about 3-dimensional collisions. That would be like explosions where things go in all 3 dimensions. That's a little bit complicated for us, but we will talk about 2-dimensional collisions. So you need to remember that the x component of a vector is magnitude cosine theta, and the y component of the vector is magnitude sine theta, where n is the number and theta is the angle. And this proper angle that it says up here is apparently, as I have been schooled by the calculus teacher, called standard position, which makes sense. So if that's what you hear in calculus, eventually I'm going to change all my proper angles to standard position. Remember, energy is always conserved, but it can be transferred out of the system. We'll tackle momentum problems with energy after the break when we talk about energy. But your momentum is always conserved, no matter what kind of collision it is. Whether they're stuck together, whether they bounce, whether it's glancing, your momentum will always be conserved. It's just going to be conserved separately in x, y components. So your initial momentum will always equal your final momentum. Your initial x momentum will always equal your final x momentum, and your initial y momentum will always equal your final y momentum. So here is a little example, which if you don't get it, it's okay, the numbers work out anyways. But let's say that you have a green ball and a blue ball. And the blue ball initially has no velocity. And the green one has some sort of momentum. Let's say that they're the same mass, just to make this easy. Let's say its initial velocity is 4 in the x direction. So it's only in the x direction. Let's say that it hits at a glancing collision and the blue one ends up going off in this direction, and the green one is going to go in this direction because it has to go in that direction. So we know that this one goes this way. You can calculate where this is going to go because the momentums have to add up. If this is true, that means that the total velocity of this one in the x direction and this one in the x direction should equal 4 in the x direction. It has to equal 4. So they need to add up. Let's say that they're both 2. If this one's 2, then that one has to be 2 because they have to add up to equal 4. Because initially it started with 4, so they have to together be 4. Initial momentum equals final momentum. Now, this one has some sort of y component to it. Let's say that it's 6 for whatever reason. This one has to be 6 as well, but it's in the opposite direction. So that when we add them up, they equal 0, because momentum has to be conserved. Because initially it had 0 y momentum, so here they have to add up to equal 0. That's why I know if this one goes off this way, this one has to go that way, because otherwise it wouldn't make any sense. Okay, so here's some pictures, kind of what I drew on the board here. Momentum must be conserved, energy is conserved, but it doesn't always say in the system here. This is a 2-dimensional collision with 2 objects hitting each other and sticking together. So this particular one is an inelastic collision. So you can see that car D hits car C. They're going to stick together and they're going to move in this direction with whatever momentum it had in the at y direction plus whatever momentum it had in the x direction, just adding them up. So that picture is not too terribly important, but here we go. So this is what we really need to do. We are going to calculate this. This is what you're going to have to do in your homework, which is why your homework is only 4 questions long. That's the best, right?
Probably long questions.
Well, you'll see, because we're going to do one. Okay, so I'm still going to give you a grid, but we're going to expand our grid. So it's probably going to take up the whole width of your paper. Just be prepared. It looks pretty much like our other grid, except for now we have vectors to worry about. So the first one is object. And we have 2 objects, so we need 4 lines. And we have a, let's see, it says a 2-kilogram green pool ball going 7 meters per second at 75 degrees hits a 1.75 kilogram pool ball going 6 meters per second at 225 degrees. After the collision, the green pool ball is going 4 meters per second at 95 degrees. What is the final velocity and direction of the blue pool ball? So we have 2 objects, a green pool ball and a blue one. So we're going to go green, blue, green, blue. Initial and final. Now, in your other grid that we learned on Wednesday, what was the next column? Mass. So we'll put mass in here. Mass is not a vector. We don't need to bring it into x and y. It's just a scalar, so we can leave it. What's the mass of the green pool ball? 2. Okay, so 2 and 2. And what is the mass of the blue pool ball? 1.7. And it doesn't change mass. It's not going to exchange mass. It doesn't talk about the masses sticking together or anything like that. So you can assume that they keep their same masses of what they started with. What's the next column that we need to make? Velocity. Now we're talking about 2 dimensions. So we need to break velocity into x and y. What was the last column that you had on yours? Momentum. So momentum is also a vector, so you also need to break momentum into x and y. And that should be your full grid. Now, we need to break this velocity because it just says 7 meters per second at 75 degrees, which is just a vector. We need to break it into components. So in the x, you need to make sure you put a cosine in all the vx's and a sine in all the vy's. This will break it into components. Now, I'm not going to do that for momentum because it will already be in components, because this puts it into component form. Okay, how fast is the green pool ball going before it hits the blue one? 7 at 75. So we're going to put 7 at 75 in both the velocity slots. How about the blue one? How fast is it going before the collision? 6 at 225. We have one more piece of information. It says, what's the velocity of the green pool ball after the collision? 4 at 95. 4 at 95. And what about the blue pool ball? Do we know anything about that after the collision? We do not. So it's going to be v at theta, v at theta. We need to know how fast it's going and what angle it's going. Okay, now comes the calculation parts. What did you do in the grid before when you filled in mass and velocity? Multiply. You do mass times velocity equals momentum. Now we have x and y here, so you're going to go mass times velocity x equals momentum x, and mass times velocity y equals momentum y. So we're just multiplying. So this is going to be 2 times 7 cosine 75. .62 and 13.5, and we're going to go, did I do that right? Let me just double check that. Yep, I did that right. Okay, 1.75 times 6 cosine 225. Two times 4 cosine 95. Okay, what do I do with the bottom one? What's this going to be? What do we do in the other ones? We just multiplied, right? And we can't really simplify that, so we're just going to rewrite it. It'll be 1.75 v cosine theta and 1.75 v sine theta. Same stuff, we just don't have numbers, so we can't put numbers in there. Okay, when you got this far in the grid, what was the next step? You add, right? Initial should equal final. So this plus this equals this plus this. So since we have the x dimension and the y dimension, we need to make sure that we do two equations. We have a velocity and a theta that we need to solve for, so two equations and two variables, and you should be able to solve. So we're going to go this plus this equals this, this, thing, there we go, plus this. And this plus this equals this plus this. And then just rewrite your numbers. So go down the x column, 3.62, negative 7.42, negative 0.70, and 1.75 v cosine theta. In the y dimension, again, go straight down the momentum y column, 13.5 equals negative 7.42 equals 7.97 and 1.75 v sine theta. Now, what's really nice about vectors here in this particular equation, we have a v cosine theta. Now, I just showed you that slide a little bit ago that said m cosine theta. What does that equal to? What does that mean? M cosine theta. What is it? Come on, guys. From the very beginning of the year, it's a vector component. Right? It's the x vector component. So if we solve for v cosine theta, it should give us our x vector component. Just this part. And if we solve for v sine theta, that'll give us our y vector component. You can substitute if you really want to, but it's a lot more work than just solving for v cosine theta and then plugging into the magnitude and direction formulas. So that's what we're going to do next. We're going to solve for v cosine theta here and v sine theta here. Not for v and not for theta. We're not going to do any substitution or elimination because that'll take a lot more work than just using it as the vector component part. So I'm going to do that over here on the side. So here's the x stuff. So this is V cosine theta, which means this is now negative 1.77 I hat. That is the x component. Now this is a V sine theta, so what is that number then? What does that mean? Say louder. It's the y component, j hat. So now you have an I hat and a j hat. How do we find magnitude?
Put it in that thing.
Yep. So we're going to find the magnitude of velocity. That's how you write that. Magnitude of velocity, which is the square root of x squared plus y squared. Now, if you're going to put this in your calculator with the negatives, make sure you put parentheses around it because your calculator is a little dumb. It thinks you want to square it and then make it negative, even though you know you don't want to do that. Or you can just leave the negatives out in this one because you know they're going to be positive anyways. If you're putting it all in your calculator at once, make sure you put parentheses around the whole thing so you square root all of it, not just the first term.
This is a
2.07. And it's a velocity, so meters per second. Now, what's next? What do I have to do to finish this up? We got magnitude. Direction. So we need the direction. We're going to find the direction of velocity. So I called it angle of V if you want. You don't have to do that. Tangent inverse of y, which is negative 1.08 over x. Now, they're both negative. What adjuster am I going to use? Plus 180. Y over x.
You're looking like something messed up. What's wrong?
In my last class I got 211. In this class
what I
I'm
got.
getting 31. Oh, because I forgot to add 180. That's why. Okay, 211. There we go. And that should be your answer right there. Now, I know it's long. I know it's grueling. It is just adding vectors. We just have to do a little bit stuff before it with the momentum. That's why there's only 4 problems today.
That's what it is.
All right. I need to fill in the last little pieces of this chapter. They threw in gyroscopic precession here and like recoil stuff, where there's no real calculations or anything. We just got to talk about it. So I'm going to go off on that tangent real quick. This is a gyroscope, and when I spin it, it has angular momentum. So I need a volunteer to come up here and hold my string really, really super tight without breaking it.
Olivia wants to.
I think Seth wants to. Come here, Seth.
So did you work today?
Not here.
So come here. You stand right here. Okay, I'm going to hand you the string, and you're going to pull it super tight like this without breaking. And make sure you face down. This is hard to turn after I put it on there. And you're going to want to hold it over this so when the gyroscope drops, it doesn't crash on the floor.
Oh, we're going to spin it. Okay.
Yeah, we're going to spin it. So just step forward, and you're going to hold the string over the table just in case it drops. All right, so hold that like this, nice and tight, up. All right, not crooked.
Oh, it's not over the table.
No, that's not spinning fast enough. It took too long.
What?
I know, we got to do a practice run. It's fine. Not everybody's as fast as I am.
Okay.
So, I tried, and I broke it.
So as well as we can.
So
I didn't do it.
Oh, I tried. It's all right.
No, try
I didn't break the string though.
No, you did not break the string. It's okay. Thank you
You want
for
it
your. Oh no, I'm not gonna try again. I'll break
Okay.
it. I'm gonna use
We
this
can keep
string.
going like all three.
Nope. Ow.
All right. Sorry, I broke your gyroscope.
You didn't break it.
I didn't break the string either.
Nope, you didn't break the string. All right. Well,
How does that mean?
there we go. Okay, so basically what happens, this is a gyroscope. It has a wheel in the side of it, and when you spin it, it's going to try to keep it in that direction that you initially had it in. And so this is the same idea as you're riding on your bicycle, right? And as long as you are going forward, you're going to stay upright. But as soon as you stop, your bicycle falls over. And that's because it has angular momentum. So it's going to keep trying to be in that direction. So airplanes and cruise ships use this, and even compasses, or fancy ones, use this to stay upright, to figure out which way is upright. So I have this here. I know it's kind of hard to see. I'm going to put it on this side so that most of the people can see. And you're going to see that it's going to try to stay in the direction that I put it.
Why did I have to do that?
When it slows down enough, it's going to fall off because it doesn't have enough momentum to keep it upright. But I'll do it for a little. It's also kind of, it's got a lot of friction. So I do have a little video for you on gyroscopic precession here that you can watch.
Hey everyone, it's me, Derek, from the channel Veritasium. And I've been following this series by Destin on Smarter every day about helicopters, and gyroscopic precession is just one of those things that still blows my mind, as it did Destin. So I'm here at the University of Sydney, my own stomping ground. I'm going to borrow some of their lecture den equipment to hopefully teach you a bit about how gyroscopic precession works.
The first thing I need to do is talk about vectors, because a lot of things in physics are vectors. That means they have direction. So an example would be momentum and force. Those are two examples of some pretty common vectors. So if I have a cart moving along here, it has some momentum in that direction, and if I apply a force to it, I can change its momentum. So for example, if I push it to the right, then its momentum will increase to the right. It all makes a lot of sense. Well, there's a similar statement we can make about rotating bodies, which is that a torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance from the rotating axis. You could call it R. So torque is the force applied times the radius away from the turning axis. Now, what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way, but the torque vector is actually pointing out this way. So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a very large angular momentum out towards the camera, out towards you. Now before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum round that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be quite friction-full wheel. So check out Destin's other videos about helicopter physics, and then come check out my channel, Veritasium, where you can find more like this. Except I don't often nearly get my head cut off by a bicycle wheel. So.
Alright, so I hope that kind of explains like angular momentum a little bit. It's going to keep doing what it wants to do, just like momentum, inertia. And that should give you a little idea of how it keeps it upright. Alright, the one other thing that I want to talk about is recoil. It's still the conservation of momentum, and just like when we had the pool ball sitting here, even though it had no initial Y momentum, when they ended up splitting, this one had a Y momentum, so this had to be the exact opposite. So if you're talking about like a cannonball with a cannon in it, if it starts at rest and then it shoots the cannonball out forwards, the cannon goes backwards. And the cannonball has less mass, so it's going to have more velocity. But it has the same momentum. The cannon and the cannonball have the same momentum. So because the cannon itself has more mass, it's going to go backwards, but not as fast. And this one talks about an astronaut in space with an oxygen tank. So he's exerting mass and velocity of the exhaust outwards, and it's propelling him in the other direction. You guys might have seen WALL-E, right, with the fire extinguisher. That's the exact same thing. That's the conservation of momentum. But since the momentums are in opposite directions, they add up to equal 0, just like the initial momentum was 0. Here's a picture of an astronaut who's shooting a gun. I don't know why he's shooting a gun in space. It must be some sort of aliens or something. But anyways, they're at 0 here. And then the bullet is going to shoot out much faster because it has a lot less mass than the astronaut. But the astronaut is still going to go backwards. Just not as much velocity because he has more mass. All right. And then your clickers aren't working right now because I got to reboot my computer to make that work. But I did want to talk about this particular question. There's not an equation for this so much as the units. The units here are important. So what I want you to do is look at the units on these two numbers. Now, it says a rocket expels gases at a rate of 1,300 kilograms a second. Now, that's kind of weird, right? 1,300 kilograms a second. What would you call that if you had to put a variable on that? We don't know. We don't have anything for kilograms per second. But what would kilograms be? Mass. And what would seconds be? Time. So it's mass per time. That's fine. That gets us somewhere. It's got enough variable for now. And then it says it's with a speed of 30,000 meters per second. What's that? Velocity. Oh, what are we looking for in this?
Force.
Yeah, what is the force on a rocket? So we're looking for force. What's the equation for force? A. Good. Now, do we have an A here? No, but what can we make A? What's another equation for A? Velocity over time. So mass could be velocity over time. Now, is this looking closer to our stuff? Yeah. So now let's just rearrange it so it looks exactly like our stuff. Is this the same thing?
Yeah.
Yep. So that's all it is. You're just going to multiply these two things together. Now, we found that all by just looking at its units. So sometimes you have all the equations you need. Just got to look at the units. So I just wanted to show that one to you because it's a little trick. All right, your homework is just these 4 problems right here, 22 through 25.
I feel like that's what problems are.
The problems